Okay. Okay, let's take this exercise. Normal distribution uses Z table. This is really kind of just what we've done before. I'm gonna skip that for a moment. I'll come. Let's see how we doing on time. We're okay on time, I think. I'm going to do this again because it's part of what we've been learning about the normal distribution. Total cholesterol values for a certain population are approximately normally distributed with a mean of two. It's a good contrast to the next problem. A mean of 200 milligrams per 100 milliliter, standard deviation of 20. Find the probability that an individual picked at random from this population will have a cholesterol value between 180 and 220. Okay, well, let's take a look. Okay, so now I'm gonna draw this. Okay, first I'm gonna take a look at what we have here. We got 200 is the mean, standard deviation is 20. So I'm gonna sketch that. I always sketch this. Okay, you don't have to if you don't want to, but I always like sketching this. Okay, so okay, here's our mean. I think I said it was 220, right? 200 means 200. Our standard deviation is equal to 20. Okay, now notice that in this problem we said population mean, population standard deviation, right? Find the probability an individual picked at random from this population will have cholesterol value between 180 and 220. Okay, 180 looks like it's about here, and 220 looks like it's about here. So 180 and 220 is how many standard deviations? It's -1 standard deviation, +1 standard deviation. Okay, I'm going to use the empirical rule to solve this because I think for our purposes right now, that's good enough. I know what's the probability that a person is going to be between 1 standard deviation below the mean and 1 standard deviation above the mean. Okay, we know that, right? 68%. Everybody comfortable with that? Please tell me you're comfortable with that. Yes? Okay, good. Excellent. Okay, let's look at the next one. Between 160 and 240. Okay, as you can guess, these are going to be the first few here are going to be really simple. 160 and 240. Okay, 160 is negative 2 standard deviations. 240 is going to be positive 2 standard deviations. So we know that's going to be 95% is going to be between of the population is going to be between those two numbers. Okay, greater than 225. Ah, things are going to get a little sticky here quick. This is 220. 225 is going to be over here somewhere, right? So we want to know what's the percentage of this population that's above 225. Well, I could just, I see that that's 25, and that's going to be 1.2, 1.4, 1.2 standard deviation. Let's actually do it. Z is equal to the value I'm interested in minus the mean over, thank you. Yeah, very good, guys. Some of you guys ahead of me. Over sigma is equal to 200, excuse me, 225 minus 200 over 20 is equal to 25 over 20, or 2.25, 2.25. Okay, so if I want to find that z-score, I'm going to go to either Excel or I'll use my table. Okay, since I think I have it back here anyway. Where did I put it? Okay, 2.25 to 2.201234 is 98.8. I'm going to round that off. 98.8. Okay, percent of the population. 98.8% of the population is going to be below 2.225 or below the z-score that it represents, which is 2.25. So that leaves 98. That's going to leave 1.2% of the population above that. Okay, good. So, oh, I'm sorry. Oh my goodness. Excuse me. You're right. It's 1.25. Excuse me. Let me go back. Like I said, I'm not a detail person. 1.20, 1, 2, 3, 4, 5, 89.4. Okay, this is going to be 89.4 below this. So this is going to be, 11.6% of the population will be above 225 cholesterol. Okay, so now let's look at what the next question is. Less than 150. Okay, so 150, let's see, this was 180, 160, 150 is going to be out here somewhere. I knew there was one that was kind of extreme. Okay, so 150, z is equal to 150 minus 200 over 20. It's going to be minus 50 over 20 is equal to minus 2.5. Okay, I hope I got that one right. So if I go back to my table and I go to the negative pages, negative 2.25, no, negative 2.5, negative 2.50 is going to be 0.006, 0.6%. So this area below 150 is going to be 0.006 or 0.6%. Okay, so got up here we got 11.6%, and down here we got 0.6%. Let's see what the next question is. I kind of got a guess that, let's see, now it's going to ask between 190 and 210. What percentage is between 190 and 210? I'm going to redraw this because it's getting real crowded here. Okay, here's my population again. Here's my mean, 200, sigma equals 20. 190 is going to be down here somewhere. 210 is going to be up here somewhere. Did I get the right numbers? Yeah, between these two. So I'm interested in the area between these two values. What percentage of the population is going to be between 190 and 210? So those are the areas I'm interested in. Now you guys know that my table works this way, that I find a z-score, and it gives me the area to the left of that z-score, right? So in order to find this area in between these two, what I'm going to do is first I'm going to do 210 and find the area to the left of 210. Then I'm going to find what percentage is in here, in other words, to the left of 190. And then I'm going to subtract this percentage, I'm going to subtract this percentage from this percentage, and what will be left is the area of the distribution, or the percentage of people that's in here. So let's go ahead and do that. 210 and 190 I'm looking up. We'll do both at the same time. 210, okay, and one's negative, right? So this is going to be, oh, I didn't calculate the z-scores, did I? This is a z-score of plus 1/2. And this is a z-score of 190 is minus 1/2, right? So plus 1/2 and minus 1/2. Actually, they're actually, I didn't draw this very well, did I? Okay, plus 1/2 and minus 1/2. So I'll take the plus 1/2 first. 0.50 is 69.2%. This is 69.2%. Okay, and let's say negative 200 minus 190 minus 200 is 10 over 20. 10 over 20 is 1/2, but it's a negative because it's on that side. It's on the left side of the mean. So negative 0.5, negative 0.05, 0.5. 0 is about 30.9, 30.9%. Okay, so this is 30.9%. So what's the difference between these two? It's 69.2 minus 30.9, which is going to be 8 carried 1, 3, 8, 2. Let's see, 3. So this is 38.3%. Right? A little, and a lot of you guys got the same answer and stuff like that. In Excel, I would, thanks for that question. That's a good question. In Excel, I would do exactly the same thing. I'd find the area to the left of, I'm going to use the function norm s dist, okay, because I already figured out the z-scores. Equals norm s dist, parentheses, and the z-score for the first number was plus 0.05, 0.5, okay, is equal to 1, equals, oh, excuse me, let me, again, I kind of shot myself in the foot there because I formatted these as whole numbers to make that other exercise easier. Let's do it 2 decimal places. Okay, that's the area represented by a z-score to the left of a z-score of plus 0.05. Let's find it for a negative z-score. Norm S dist, parentheses, z-score this time is negative 0.5, and that area is 31%. And the difference is going to be 69% minus the 31%, or 38%, which is about what we got before. Okay, so you can do this in Excel. You can do this with a table. You can do this with tables online and so on and so forth, calculators. Some calculators have statistical functions. You might be a little, on the test, you might be a little bit limited in terms of using stuff that's on the internet. You'll be allowed to bring in, it's basically, most of these tests are basically open book, but we might be a little bit restrictive on what might be on the internet. You'll be able to use Excel and SPSS and so on and so forth. Okay, so now I'm going to take a look at this next problem, which is a bit different. Okay, applying the central limit theorem. Central limit theorem. I'm dealing with a sample now. Okay, a sample of size 25 is taken from the population above. What is the probability that the mean of the sample is larger than 204? What is the probability that the mean of the sample is between 192 and 204? So on and so forth. So dealing with we're dealing with a lot of looks at what we think the sample should look like from this population. Well, we know the population mean is 200. We know that the population standard deviation is 20, right? That's important because a lot of times we don't know the population standard deviation. In this case, for the central limit theorem, in order for us to apply this formula, sigma over the square root of n, we need to know the standard deviation of population. Kind of a little, remember we're still, this is a learning exercise that we're doing here. It may not represent most of the conditions that we'll be in when we actually do this kind of work, and we don't know the population standard deviation. We have to deduce it based on our sample. For the time being, for this week only, or for the next 2 weeks, let's say, we're going to know the population standard deviation. So the question here is, we're going to take a sample of size 25 from that population. What's the probability that the mean of the sample is larger than 204? Let's start with that question first. Okay, I'm going to get my pad up. So the mean, say standard, sample size is 25. Okay, I'm going to go over here. I'm going to start with a fresh page. Okay, so I'm now going to sketch out what I think the sample distribution is going to look like. Okay, sample distribution, if I take repeated samples of size 25, I'll get one number, I'll get another number, I'll get another number, I'll get another, and I'm going to put them all together and show them as a distribution. Okay, so if I take repeated samples of size 25, what do I think the mean is going to be? If I take samples over and over again, like hundreds of times, thousands of times, what do you think? Yeah, the mean is going to be approximate the mean of the population. It's going to be 200, just like the population. Well, now, remember, the standard deviation of the population was 20. What do I think the standard deviation of this distribution is? The sample distribution. What do I think that standard deviation is going to be equal to? Anybody remember the formula? Okay, it's going to be sigma over the square root of n. Or in other words, it's going to be 20 over the square root of 25, which is 5, which is equal to 4. The standard deviation of this distribution is 4. Okay, so now when we consider these values, okay, the probability of getting a sample, taking a sample at random of random people from the population, the probability that that sample is going to have a mean that's more than one standard deviation below the population, or another below the rest of our samples, or 196, and the probability that it would be above one standard deviation above, or 204, probability that's between these two is going to be 68%. Probability is going to be greater than 204 is going to be, let's see, 32, so it's going to be 16%. 16%, and so on. The exact numbers you would apply the same z table as you did before, except this time we would be applying it to the sample distribution. Okay, so what was the exact question? The exact question was, what is the probability that a mean of that sample is larger than 204? Well, we just answered that, didn't we? 204 is one standard deviation, right? X minus X bar this time, because we're dealing with the average, over the standard deviation, not sigma. Okay, that's going to be 204 minus 200 over 4, it's going to be equal to 1 standard deviation. So we know that this is 68%. This area in here is going to be 34%. Okay, and it's going to leave 16% for this area up here. Okay, I got 200 because my repeated samples from that, remember the population, remember this is the same population we were dealing with in part 1, where the mean of the population was 200. So if we take repeated samples over and over again, hundreds or thousands of samples of the same size, and we made a new distribution, we would expect it to have the same mean as the original population did. In other words, half the times the samples would have a value below the population mean, half the time it'd have a population a mean above the population mean. Do you get that? That makes sense to everybody? Okay. What happens is that what we're looking at here is the way that it would look, if we took repeated samples over and over again of that size 25. Okay. I'm gonna let's go up to the next part. What is the probability of the mean of the sample is between 192 and 204? We're using 204 just for the the only reason we're using 200 here is because they mention here that a sample of size 25 is taken from the population above, and we told you that the population above had a mean of 200, and also told you that the standard deviation of the population was even more important because we need that to calculate our sample distribution standard deviation. Okay, just for this exercise, we're taking it from there. Okay, so now where'd I go? I got the wrong page here. Here we go. I'm going to get this thing back up here. Okay, so what was I looking? 190, I think it was. What's the probability? I'm going to have to take another look. I forgot. I'm so easily distracted. What is the probability? Let me move this over. You can see it. I got stuff on my screen that's blocking my view that you guys don't see. Probability 192 and 200, that's between 192 and 204. Okay, so we know that this is about 16. 190 is going to be over here. So 190 is how many standard deviations below, was it 190 or 192? 192. Wow. I'm really losing my mind here. Okay, 192. It's tough getting old. Paul Newman was famous for saying, getting old is not for sissies. 192 and 200. So we're 2 standard deviations. Minus 2 is our z-score here. Plus 1 is our z-score here. We already know that this area is about 16. This area is about 34%. So if this 2 standard deviations below the mean, we know 2 standard deviations below to 2 standard deviations above is 95%. That leaves about 2.5% in here. Just same stuff we've done before. So this area is 2.5%. This area up here is 16%. So we've accounted for 18.5%. So what's left is between these two numbers. It's going to be between here and here. Okay? Or it's going to be 81.5%. 81.5% of the means. If we took samples over and over again, 81.5% of the time, we would get a value for the mean of the sample that we took of size 25 between 192 and 204. See, what we're learning now is probabilities, what we can expect when we take a sample of a certain size from a population. And we're going to be doing this, and we're going to be doing this all the time. It's going to become more and more important. Let's take a look at the next part here. If we took repeated, okay, it was probably if we took repeated samples of size 25 from this population, within what range would we expect 95% of the sample means to fall? Do this twice, once with the empirical rule and then use the z-table. Okay, I'm going to draw this again because this is a great question. Okay, let's test our knowledge now. Okay, here's my sample distribution. Okay, based on sample distribution, based on taking samples of size 25 from that original population where sigma was equal to 20, the sample size of 25 means our standard deviation for this is going to be 4. So our mean of all the samples is going to be 200. Our standard deviation for the sample is going to be 4. Okay, if we took samples from here, where would we expect 95% of the samples of size 25 to land? What number to what number would we expect to contain 95% of the samples that we would get? In other words, only get a number less than this 2.5% at a time. Only get a mean from our sample size of the sample of 25 that's higher than this 2.5% at a time. What do we think these two numbers would have to be? Anybody want to hazard a guess? What would be the z-score of these two numbers to capture 95% of the means that I would get? Okay, I already got an opinion there. The actual numbers, yeah, because you guys realize negative. If I use the empirical formula, it's -2 to +2. 95% of the time, I would expect to get a mean between 2 standard deviations above and 2 standard deviations below. In this case, 192 to 204. 204? 204. No, 208. 208? 208. Okay, 95% I expect to. So that means, in other words, that getting a sample, if I took a sample of 25 people from this population, if I got a mean of 209, that would be unusual. I wouldn't expect that to happen very often. I wouldn't expect to get a mean of 189 very often, right? That would be relatively, especially 189 because it's way down here. That would be a relatively rare occurrence. That's important, right? That's what we're doing here is we're figuring out what's the likelihood that we would get means that are so extreme that we would expect them to come up very rarely. Okay, this is going to be the basis for the way we make judgments later on as to whether one group has a different mean than another group based on samples, based on not knowing the entire population, but based on knowing the way their sample, a sample from that population compares with the other. Well, now I'm going to ask you, remember I said I wanted to do this two-way. I wanted to do this using the empirical formula. Now I want to do it using the z-table. Okay, and what I'm going to do here is I'm going to get the z-table out, and I'm going to look at what z-score I need in order for me, I think I'm pressing against something. That's what it is. Okay, I was leaning against the tablet. Okay, I'm going to look up what z-score I need in order to have an area over here of 2.5%. In other words, we want 95% in the middle, we want 2.5% on the bottom, 2.5% on top. So I need to know what z-score will give me 2.5% here. Okay, so that would be, let's look in here in the areas. See 1.2%, 2.12, 2.0, 2.50. In order to get an area of 2.5% in here, I would have to have a z-score of, now I'm going to find it again, 1.90123456. Not 1.96, negative 1.96. That z-score is not really, remember the empirical formula is not really uh, um, the most accurate prediction. It's an estimate. Really, it's a z-score of negative 1.96. And if I go on the other side, remember I'm going to need, in order to get 2% here, this is going to have to be 97.5%. Right, I'm going to go over here to the positive numbers. Okay, 97.5 is going to be 1.9. What do you know? 1.96 again, positive. right? Positive 1.96, right? So really 95% of the sample outcomes are going to be between negative 1.96 standard deviations below the mean and positive 1.96 standard deviations above the mean. That number is going to come up very shortly. We've been using this kind of as a crutch, this empirical formula, -2 and +2, -1, +1. We're going to start to demand a little bit more accuracy of ourselves. So really, that 95% between these two values is really 1.96 standard deviations, not 2 standard deviations. Similarly, with 1 standard deviation, it's not really 68%. It's a little bit more complicated, a little bit more complicated fraction, a little bit more defined fraction. Okay, so now let's go back and take a look at the next part of this problem. A sample size of 100 is taken from this population, from population. What range would we expect 95% of the samples to fall? Like I'm only going to do it one. Well, I'm going to do it using. Well, it doesn't matter. We can do both ways. Okay. This time, instead of remember before we said, I'm going to get one more last piece of fresh paper. Okay, as a distribution. Okay, means 200. This is a sample distribution. Okay, the mean is equal to 200. The standard deviation is equal to 4. These are our sample. This is our sample distribution, not our population distribution, and that's based on a sample size of 25 standard deviations. For really, sigma was 20 for the population. Remember that. Okay, so now before we said, okay, our values here. We want to know what range of values that 95% of the outcomes would fall. And we know that by looking at our z-table, that would represent the value that is 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. You could use -2 and +2 if you're doing it round. So yeah, 180. Well, hang on a second. We haven't done it yet. Okay. So what is 2 standard deviations below the mean? Remember, standard deviation is 4, right? Standard deviation of the population is 20. Standard deviation of the samples is 4. So 2 standard deviations below the mean. This would be approximately 192, and this would be approximately 208. But we're going to calculate it a little bit more accurately. It's going to be 200 minus 1.96 times 4. Okay, what is that equal to? That's equal to 192 point, let's see, 192, I'm subtracting, it's 24 less, 0.76, no, excuse me, 192.24. Did I get that right? Oh, hang on a second. Don't get ahead of me. I'm still doing sample size of 25. You guys are way ahead of me. You know that? Okay, 191. Hang on a second here. I get my calculator up so you know I'm right. 1.96 times 4 equals 7.84 minus 200 equals 192.16. Excuse me, 1116. Right? So this is going to be 192.16. Yeah, with the empirical formula would have just said 192, and this is going to be 207.84. Okay, because 1.96 times 4 instead of just 2 times 4. Okay, so that's the range. This is the range within which I would expect 95% of my sample means to fall if I took a sample of size 25 from a population as standard deviation of 20 and a population mean of 200. That's where I would expect 95% of my samples to fall. This range is called the confidence interval. Okay, we're getting a little bit. Did you guys hear the word confidence interval during the lecture? Did that come up during the lecture, confidence interval? Okay, nope. Okay, I'm not going to go into it then. But just keep in mind in the future, we're going to look at this range, 2 standard deviations, 95% of the outcomes. We're going to look at this as what we call the confidence interval. It's the interval within which we would expect most of the samples to occur, given what we know about the population. Most of the time, you're taking a sample from the population. You don't know what the population mean is. You don't know what the population standard deviation is. So you use the sample to estimate the standard deviation, use the sample to estimate the mean, and then you use this range of 95% to estimate what the true mean of the population is. In other words, if your sample comes up to be 201, you would say, well, okay, this time when I took it, I sampled 25 people, I got an average of 201. Now I'm going to say, well, 95% of the time, given that that this came from a sample where the population had the distribution that was in my sample, I'm guessing that my confidence interval is somewhere between 192 and 208. In other words, I may have found 201 here, but I'm 95% sure the real population mean is between 192 and 208. The confidence interval gives you a way to quantify what your level of confidence in the your prediction of the mean is based on what your sample did. Really, here we're not really doing that yet. We're looking at the distribution of the samples because we know all about the population. We know what the mean of the population, standard deviation of the population. Let's add a twist to this. What happens instead of, I lied, I'm going to do this one more time. Okay, what if instead of, remember the population, this is based on 200 and sigma is equal to 20, right? What if, and again, we take a sample. Let's say this time we take a sample of 100, right? So this time sample size is 100. The mean of all the distribution of sample means is the same, so it's still 200. What's the standard deviation for a sample mean for the samples for the distribution of samples of size 100 instead of size 25? What's that? What is that equal to? Okay, it's 20, right? Excuse me, 20 divided by the square root of 100, okay, which is 10, is equal to 2. Okay, we all agree with that, 2? So now if I asked you, what range would we expect 95% of the samples means? Same population. So this time the only thing that changes is we change the sample size. What range would we expect 95% of the sample means to have, right? If we took a sample size of 100 instead of a sample size of 25. Well, in this case, we're going 2 standard deviations to the right, to the left, 2 standard deviations to the right, except this time a standard deviation is 2. So if I use the empirical formula, this is 196 now, and this is 204. 204, right? Or actually, if I were going to use 1.96, it would really be 196.08 or something like that, right? I think. Let's see, 1.96, 02, and this would be 203 point, right? 2 times 1.96, 203, we 203.92, right? Be something like that, close enough, right? I'll let you guys actually work out the actual math there. You see what happened here? This is our prediction of what 95% of the samples would look like based on our distribution of this mean, right? Our sample size allows us to narrow the range that we would expect these sample means to be if we took repeated samples. That also means that if we didn't know anything about the population, the bigger the sample size is, the narrower that can be our confidence interval for predicting the actual mean. Right? That makes it more valuable. If I can say that I'm 95% sure the mean is between 196 and 204, instead of saying between 192 and 208. Right? That's more valuable than that wider range. That wider range is less informative to me. Okay, so that's what we're dealing with here. We're learning to understand how samples behave, random samples from a population behave, and how we can use that to our advantage to make predictions about that population from the sample. and to understand how confident we can be in what that sample predicts the population mean to be. Now, the next step is we're going to use that to compare two different populations. Is the cholesterol level of Frenchmen different than the cholesterol level of Americans? We're not going to measure every American. We're not going to measure every Frenchman. We might do a survey and measure 100 Frenchmen and 100 Americans, but then we need to know uh, 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 what the level of confidence is of the mean that we find in a sample for Americans and the mean that we find for uh, uh, Frenchmen. By the definition of confidence for us is a range, right? In other words, we're 95% sure. Remember, we're getting ahead of ourselves here. This is not really what we wanted to cover. The real thing that we're interested in here is understanding how sample distributions operate. But I'm just saying that, like, just to give you a little heads up of what's coming. We're going to use this to, if we took a sample, one sample. Remember, this is the way repeated samples over and over again would look like if we plotted their distribution. We're really in real life only going to take one sample, and based on that sample, we're going to make predictions about the mean of a population. Understanding how samples behave is going to allow us to not just take 100 people, calculate the mean, but also apply a level of certainty to that mean. In other words, I got the number 27 for the mean, but because I understand what the standard deviation of the sample is and how that relates to the sample size to the population, I can say I'm 95% sure the real population mean. Remember, when you take a sample, you don't know that you've gotten the population mean. The real population mean is between 25 and 29. Now you can take that knowledge, your level of confidence that you're 95% sure that you're in that range in predicting the population. You can compare it to another population and say and have a level of certainty whether and know what your level of certainty is or what your chance of error is if you say, well, I think it's different from this other population because I expect it to be between these two numbers. But we're getting a little bit ahead of ourselves there. Okay, so I'm just looking back at some questions here. So two times Z-score. Alex, I'm not sure what that is. Standard deviation 2 times the Z-score 2. Oh yeah, 4 plus or minus 4. Except that instead of using, I used 2 for the standard deviation, but instead of a Z-score of 2, which you would use if you're doing the empirical formula, you would use 1.96. Add or subtract 1.96. So instead of getting 196 to 204 in real life, if we did this, because we'd be doing it more accurately with Excel or with the Z table, you would get 1.96 point something to 203.9 something, right? So that's the 1.96, 196.2 came from 200 minus 2 times 1.96, which is a little less than 4. So that's actually a little less than 4. It's not shouldn't be 0.02. It's 0.04. 1.96 times 2, you lose 0.4. 0.4. 1.9. 1.96. 0.08. I think it is. Right? Should be 0.08. You can actually do the math. It should be 1.96 times 0.08. And on the other end, it's 203.92. In other words, 200 plus 2 standard deviations, the standard deviation to 2 times a z-score of 1.96. Okay, so that comes out to 203.92. Okay, so our range there for 95% that we would expect 95% of the sample means to fall is from 1.96.08 to 203.92. Now, there are some other examples there that, like this first one, you can play around with these, and maybe as part of the, I'll post some answers for them as part of the exercise. This involves a proportion. Number 2 involves proportion. I think, as far as I could tell from the slides, Professor Waldron just barely introduced proportions, so I'm not sure that would wind up on the test. So You got to look at that, but I would hold off on dealing with a proportion that's going to come up later on. But these others you might have a shot at, I think. Um, 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 if you see this thing called t-value, skip that. Don't worry about t-values and stuff like that. But for the most part, stick with what we did tonight. Go review what we did tonight, and I'll throw up a couple of other examples and so on and so forth. It's two. Remember, this was kind of a funky example because the standard deviation and the z-scores came out roughly the same. Standard deviation was 2, right? And 2 standard deviations below the mean is 2 times 2 or 4, 196. But it's really two standard two. It's not really 2 standard deviations below the mean. It's 1.96 standard deviations below the mean. Yeah, I'm sorry. You guys are explaining. You don't even need me here. You're explaining it to each other. I appreciate that. But I still don't get 1.96 instead of 2. Well, remember that the empirical formula says that 95% of this, any normal distribution, 95% of it is between 2 standard deviations below the mean and 2 standard deviations above the mean. That's only an estimate. That 2 standard deviations below the mean to 2 standard deviations above the mean is really only an estimate. It's really 1.96 standard deviations below the mean and 1.96 standard deviations above the mean that contains 95% of the distribution. The empirical rule is just an estimate. Okay, it's not a law. In other words, empirical rule is an estimate or a guide. It's not really the exact number. The exact number is actually 1.96 below, 1.96 above. So if the standard deviation is 10, right? 1.96 standard deviations, 1.96 standard deviations to the left of the mean would be 1.96 times 10, or 19.6 instead of 20. And 1.96 standard deviations above the mean would be 19.6 instead of 20. Okay, it's just a more accurate way. Is the real number exactly right? Exactly right. Okay, so I think we're